Okay, so we look at question C. So figure Q12, okay, Q12. So this is the figure Q12, okay. So show a spherical shell and infinite long wire charge distribution. Okay, so this is the wire, the line. Okay, and this is the spherical shell, okay. Okay, so the center of the spherical shell is this one, the center. Okay, the coordinate is given. Okay, inner radius A, okay, A radius, B is this one, and the volume charge density rho V is 2 nanocoulomb per meter cube. Okay, so the long wire is located along the z-axis. Okay, it's a long wire. Okay, so it's an infinite length. Okay, infinite wire. Okay, and the rho L is given by this one. Okay, so first derive the electric field formulas for the wire. Okay, and the second one is derive the electric field formulas for the spherical shell. Okay, and both by using the Gauss law. And for the second one, it only want you to derive the electric field when the R is greater than the B. Okay, so here you have to put in the steps of derivations that we learned in class. Okay, so we go for the first one. Okay, that is about line. Okay, line. Okay, so your line, okay, and let me draw this axis. Okay, so this is the axis. So this is your line. Okay, infinite line, right? The length is very long, infinite line. Okay, so this line has charge. Okay, so this charge will produce electric fields that is going to outward directions. Okay, so when we want to know the electric field anywhere around this line, we have to build a Gaussian surface. Okay, because of the shape of the line is like a cylinder, so our Gaussian surface will be a cylinder surface. Right, cylinder surface. So just draw a cylinder. Okay, you draw a cylinder. So this is cylinder. And from the top view, okay, this one will be your line. Okay, and this one will be your Gaussian surface. Okay, this is the top view. Okay, the top view. So the electric field will be going outward in these directions, right? Okay, in the R directions. Okay, right. So to derive the electric field formula using the Gauss law, first we must know what is the Gauss law. So the Gauss law says that the total electric flux density, okay, that coming out from the Gaussian surface, okay, is equals to the charge that is enclosed by the surface. Okay, so look at this cylinder. Basically, it has three surfaces. Okay, one is for the top, okay, right, and one is for the bottom, right. Bottom you have one surface, and also you have one side, right. So top is over here, bottom is over here, side is over here. Okay, since the line is infinitely long, okay, so we don't consider, okay, the top and also the bottom flux coming out. Okay, and we will only focus on the flux that is coming out from the side. Okay, so from the side, okay, so we have surface integral, and for the electric flux density, we are using cylindrical coordinate. Okay, so this is unit vector R, and then for the ds, it will be R, dphi, and dz. Okay, so this is the dx representations for cylindrical coordinate. Okay, and we are choosing the R directions. Okay, so we are choosing the R directions. Okay, so this one is for the left side. I focus on the left side first. Okay, left side. Okay, so for this dot product, you can remove it, right? Dot and dot, you get one. Okay, and then for the phi, okay, phi is the angle of the cylinder, so it is 0 to 2 pi. And for the Z stands for the height of the cylinder. Okay, so in this case, I will just apply a parameter from 0 to h. Okay, so you can perform the integration. So you will get a d r 2 pi and h. Okay, so this one is for the left hand side. This. As for the right hand side, okay, because the line, okay, is not given the q, they give you the rho l. Okay, so the q equals to integrate rho l dl, right? Rho l dl. Okay, so the l over here is the length, okay, the length of your wire. Okay, so it will be dz. Okay, dz. So rho l and dz. So your z will be from 0 to h. Okay, so it will be rho l h. Okay, so this is the right hand side, left hand side. Now we put them together. dr 2 pi h equals to rho l h. Okay, we put it together because this one is the Gauss law. Okay, Gauss law. So right hand side, left hand side, we put it together. Okay, and then we can cancel the h. Okay, so our d will be rho l over 2 pi r. Okay, 2 pi r. And the direction we can insert. Okay, as for the e, okay, just top up with the epsilon because the d is equal to epsilon e. Okay, so just top up one more epsilon. Okay, one more epsilon, then you can know the answer. Okay, so rho l over 2 pi epsilon r. Okay, so this is the derivations, okay, of the electric field for infinite wire. Okay, right, so this is question number 1. Question number 1. Okay, so we go to the question number 2. Okay, derive the formula of a spherical shell. Okay, so spherical shell. So remember, the center of the spherical shell is 0, 2, negative 2. 0, 2, negative 2. It's okay. We don't draw the coordinate system. We just draw the shell first. Okay, so inside is nothing. Then we have this outer. So it's like a donut. Okay, so over here is the A and over here is the B. Right, so this is the region that has the rho V. Right, inside there is no rho V. Yeah, inside here there is nothing. There is nothing inside. Okay, only outside we have the rho V. Okay, we have the rho V. Okay, so we are going to apply Gauss law again. So this is the Gauss law. Q. Right, so where is the place that we want to find the electric field? We want to find the electric field where for the area, for the region that the R is greater than the B. So we must construct our Gaussian surface, which is the red color one. Okay, my Gaussian surface. Okay, and this is the R, right, greater than the B. Okay, so because you have the rho V inside, so the electric field, they are moving outward in these directions. Right, outward in these directions. Okay, so this is your electric field direction and also your electric flux density. Okay, so now I'm going to do the left hand side. So for the D, it is in the R directions. Okay, capital letter R because the shape is spherical shell, so I'm using spherical coordinate system. Okay, and for the DS also, I have to apply the coordinate system for the spherical, okay, for the sphere as well. So it is R squared sine theta, d theta, and d phi. Okay, I'm focusing on the left hand side, left hand side. All right, and then you have a directions. Okay, so the direction can cancel. So the d theta will be d 0 pi, 0 2 pi. Okay, So you know you are going to get dr squared 4 pi. Alright, so this is for the left hand side. As for the right hand side, so they give you the rho v. Okay, so rho v. So you are going to expand this dv according to the spherical coordinate systems. Okay, so the rho v value in the question is 2 nanocoulombs. Okay, 2 nanocoulombs. Okay, so 2 nanocoulombs. Okay, and then for this, it will be r squared sine theta d theta d phi. Okay, and also dr. Okay, dr. Right. Okay, so for the theta is 0 to pi, 0 to 2 pi. Okay, and for the r, okay, okay, it depends on the shape. Okay, it depends on the shape of your spherical shell. So you will be from A to B. Okay, A to B. Okay, so now you can expand this one. Okay, so for this part, you can, okay, let us do the integration for the theta first. Okay, here got theta, sine theta. Okay, so this one is you integrate. So remember, change your mode to the radian. Okay, integrate sine x, and then from 0 to pi, you are going to have 2. Okay, so quite similar. Okay, so you have 2 nano r squared. Okay, and then you have 0 to pi, and then you get 2, right? Okay, and next you get 2 pi, right? You get 2 pi. A and B, and then you get 2 pi and 2, right? And dr. So you can combine is 8, no, 8 nano pi, and then you integrate A and B, r squared dr. Okay, right. So next, you can continue. If you want to insert the value of A and B is fine as well, because the value is fixed value. So let's say we want to insert the value of the A and B. So A is what? A is 1 meter, B is 3 meter. Okay, 1 and 3 r squared dr. Okay, so by doing so, okay, you can simplify your things. Okay, it's 3, 1. You can use calculator. So you get 9. So it's 72 nano pi. Okay, 72 nano pi. And this is the right hand side. Now we put the left hand side and the right hand side together. Okay. So equals to 72 nano pi. Okay, and D is equals to 72 nano pi over 4 pi r squared. Okay, you can cancel this. Right, the r directions. As for the E direction, okay, you can simplify to become 18. So 18 nano over epsilon r squared. Okay, so that would be your equations, okay, for the electric field when the R is greater than B. Okay, now we go to the third one. Calculate the total electric field at these positions. Okay, at these positions. So we have to apply the formula that we have derived just now. So the first formula is this one, okay, coming from the wire. Okay, and the second formula is this one, and it's coming from the spherical shell. Okay, so you have to find the E total. okay, that is the E from the line, right, plus the E from the shaft. Okay, so for the E from the line, okay, so EL. So what is our EL formula? EL is rho L, okay, rho L over 2 pi epsilon R and R. Okay, so the first thing is to find these R. So our observation point is what? Our observation point is 0, 2, 3. 0, 2, 3. So how to find the R? How to find the R? So you need to find a point T, right? Find a point T. So if you cannot imagine, you can draw the diagram again. Okay, you can draw your line. And 0, 2, 3, 0, 2, 3 is here, observation point. Right, so now you need to find the R. Okay, so this is your point T. Okay, so point T, the value of the X is 0. The value of the Y is also 0. As for the Z, it will be 3. So your R is equals to 0, 2, 3 minus 0, 0, 3. Right, so you have 0, 2, to Y. Okay, to Y. Okay, and this, the amplitude, no, the magnitude is 2. Okay, and the unit vector R will be Y. Okay, unit vector R will be Y. Okay, so now you can replace the value. Okay, replace the value. Okay, so rho L is, what's the value of rho L? Rho L is 12 nanocoulombs. Wait, this one just now I replace it with what? 2 nano is correct. Okay, 12. Okay, it's 12. Okay, so the EL is equals to 12 nano, right, over 2 pi epsilon naught, and the R is 2. Unit vector R is Y. Okay. Okay, so what's the answer? It is 3 nano. Okay, so it's 107.85. Okay, volt per meter. And in the Y directions,